Hi everyone and welcome to the 19th lecture of our CS2100 District Scratchers course. So in this part 1 of the 19th lecture, we're going to introduce so-called expected values. So let's get started. So here is the outline of the lecture. So first we are going to introduce the concept of random variables. Then we'll tie those to expected values. And finally we will show a few expectation rules. So a random variable is a measure of numerical values associated with possible outcomes of a probability experiment. We typically use x to designate a random variable. As an example, x can represent the number of children in a household in one apartment building. And then the possible values for x can be drawn from a set such as 0, 1, 2, 3, 4, and so on. As another example, x can also represent the possible rolls of a die. And finally, x can represent the sum of possible rolls of two dice that are rolled in an arbitrary order. For a given probability experiment, let x be a random variable whose possible values come from the set of numbers x1, x2 to xn. Then the expected value of x, denoted by e of x, denoted by e of x, is the following sum. Sum of I is equal from 1 to n, xi times probability of x when it's equal to xi. And when this expands, you get this expression. So the expected value of x is also called the average value of the random variable, meaning the average of the values x take on over many repetitions of the experiment. So let's apply this on an example. We want to compute the expected value on one roll of a fair die. So x are the values that the roll can take, and we assume that we have a 6-sided die, and so the values range from 1 to 6. Then we can compute the expected value as 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 and so on, which amounts to 3.5. As another problem, we can look into what is the expected value on one roll of a loaded die, where the probability of rolling 1 to 5 is 1 over 10 each, and the probability of rolling 6 is 1 over 2. Then the expected value is computed using this sum, where we plug in these probabilities and the values that the die rolls, and this computes into 4.5. So as expected, because the die is loaded towards 6, the expected value goes up. So here is another example problem. So suppose we pay $2 each time to play the following game. We roll 2 fair dice and collect $5 for each 6 that comes up. So if we are paying $2 each time we play, do we expect to win more than we pay if we play many times? So in this problem, x is the amount we can win on a single roll of both dice, and x is drawn from the set 0, 5, and 10. So 0 if there are no 6s, 5 there is 1 6, and 10 if 2 6s come up. Probability that x is 0, which is the probability where there are no 6's, is 5 over 6 times 5 over 6, which is 25 over 36. Why 5 over 6? Because there are 6 possible outcomes, and 5 of them are not 6's. Probability that we roll 1 6 is choose 1 out of 2. So we pick in which place we roll the 6, the first or the second, and then we multiply this with the probability that we roll the 6 and the probability we did not roll the 6. And finally, the probability that we roll 2 6's is 1 over 6 times 1 over 6, which is 1 over 36. And now we can compute the expected value of x as 0 times 25 over 36 plus 5 times 10 over 36 plus 10 times 1 over 36, which is equal to 1.67. So this is the expected outcome. And because 1.67 is less than the $2 that we are putting in, this tells us that we should not play this game. We will be earning less money than we are putting in. So this is a nice example of how we can leverage probabilities and the theory behind them to figure out whether it's worth playing some game on chance or not. Okay, next we'll introduce a couple of simple expectation rules. So let x and y be random variables, and let a be a scalar value. Then the expectation is linear, and here are 3 rules that capture that. So expectation of a times x is equal to a times expectation of x. Expectation of a plus x is equal to a plus expectation of x. And expectation of x plus y is equal to expectation of x plus expectation of y. Okay? So let's see how we can use these rules on example problems. So in the first one, an experiment consists of tossing a coin 3 times. Let success x when x is 1 be heads, and failure when x is 0 be tails. Now the question is, how do we compute the expectation of 3x? And recall from the previous slide that the expectation is linear. So expectation of 3x is equal to 3 times expectation of x. So that is equal to 3 times, and then expectation of x is 0 times probability that x is 0 plus 1 times probability that x is 1. Because it's a fair coin, probability of both of these outcomes is 0.5. So we plug these numbers in, and we get that the expectation is 1.5. Okay, here is another example problem. Suppose teams A and B play a best of 5 series. In other words, they play until a team has won 3 games. And team A has a 1/4 probability of winning any given game. What is then the average number of games in the series? So our random variable x is the number of games in a series. So value x can be from the set 3, 4, or 5. In this problem, we have no preference as to who wins. So probability that the series has 3 games is 1 over 4 to the power of 3 plus 3 over 4 to the power of 3. So that's computing the configurations when team A wins all 3 games or team B wins all 3 games. probability that the best of 5 series has 4 games is choose 3/2 times 1/4 to the power of 3 times 3/4. So this captures this setting on the right when team A wins. That means that we have to place 2 A's in these 3 available slots. That's why we have choose 2/3. And then we have to compute the probability of this whole configuration, which has 3 A's. So it's 1/4 to the power of 3, and it has 1 B times 3/4. And we have a similar probability for the case when B wins. So this is this other expression. We are also choosing 2/3, but now we are placing 2 B's into 3 slots. And then the probability is 1/4 because there will be 1 A times 3/4 to the power of 3 because there will be 3 B's. And finally, probability that we have 5 games is 1 minus probability that we have 3 games plus probability that we have 4 games. Okay, and then we can compute the expected value for x as 3 times probability that x is equal to 3 plus 4 times probability that x is equal to 4 plus 5 times probability that x is equal to 5. And when we plug these numbers in, we get that is equal to 3.77. So the average number of games in the best of 5 series, if the probabilities of winning are set as in this problem, is 3.77.